All right, so before we get started on this presentation here, I just wanted to give a quick thank you and a sincere appreciation to Stu McMillan and the Altus Group for having me a part of this project. I'm really excited for what we have within this course, and for me personally, this was a little bit of a different challenge and application for some of these fascial conversations, and it was actually something that was very enlightening for me to put together. So hopefully there are some things in here that are helpful for you all and things that you can take and apply directly. But for those of you who aren't familiar with my work, I've been, diving into the fascia concepts and the fascial anatomy for a number of years now. And although my work primarily revolves around injury restoration and return to play concepts, I think fascia, being that it is just another biological system that we possess, has tremendous applications across all aspects of sports performance, and that also includes for the sake of speed. At their foundation, sports are derived from really three central pillars. We have skill acquisition and execution. We have movement adaptability and bandwidth, or problem solving within sport. And then we have motor processing and movement speed or velocity. At the end of the day, we can go through any specific sport, whether it is sprinting or it's something more team-based, football, basketball, baseball, whatever it may be, and we can see outliers in any case. There are players that have made it to the top level and performed at the highest levels that didn't check boxes A, B, and C, or didn't have certain strength profiles, didn't have certain physiques or anthropometrics that we would typically see within sport. But I think when we get down to the nitty-gritty of it, we cannot go through our archives and find anybody who's made it to the professional or elite levels without being able to possess a very profound ability for skill acquisition and then execution. And then I would take that a step further in saying that reaching the elite level is going to require athletes being capable of moving at high velocities or producing great forces in short periods of time. As S&C coaches, I think we've been pretty poorly misled into thinking that strength or doing more volume, more intensity, or just increasingly putting more accumulation on the athlete is going to solve problems. And as we should know, that's just not the case. Increasing force output is extremely important for athletic performance, but at the end of the day, this isn't a panacea for all things improvement. And I think that we need to see our role as strength and conditioning coaches and human performance coaches as being a little bit more diversified. Taking that a step further, I think we've also been misguided or misled in the anatomy realm in thinking that our work is entirely operative around musculoskeletal anatomy. And as we'll cover throughout this presentation, and as I've talked about for a number of years now, there's just more to this puzzle that we're trying to solve. And this isn't to suggest that our science is wrong. It's just to suggest that we are at an incomplete state with human performance and development, and that we need to continue to unravel some of these things that are a little bit more intricate or nuanced. In this webinar, we're going to discuss and demonstrate how the fascial system is intimately influential for not just speed acquisition, but really for movement and high velocity movements in general. And then really just taking a look at how this unique anatomy is interspersed and interrelated to all of the conventional things that we've all been introduced to and developed our work around. So for all intents and purposes, our work has been derived from the construct of biomechanics, or the physical applications to the human body. And although that this has come a long way over the last 50 years, once again, I think that we're just at a point where we have a pretty decent understanding of certain things, but there's still so much out there that we really don't have a good grasp of. And quite frankly, we turn a blind eye to a lot of it. I think that for the most part, the biomechanics and the concepts of linear forces, musculotendinous anatomy, and longitudinal force transmissions have been pretty thoroughly studied. And I think for the most part, we all have a reasonable level of agreement across these things. But on the opposite end, when we talk about biotensegrity, which we'll cover in a little bit more detail here in this presentation, I think these things are a little bit less understood, to include nonlinear movements and force transmissions, lateralization of force. Once again, the general concept of the myofascial anatomy is something that has been pretty neglectful throughout the course of our entire industry. And while we have a continually building and relatively deep understanding of the musculoskeletal and tendinous anatomy, I think without understanding these myofascial concepts, we're really just working at a reduced cost. We're putting too much into one part of the body or into certain systems of the body while completely ignoring this other one that happens to have a tremendous influence on how we move and how we perform in sport. The premise of this, and this is something that Altis and Stu and Dan have talked about extensively for years, so I'm just piggybacking on this, but I think it's extremely important that we understand the body as being an integrated system of systems. The musculoskeletal anatomy is important, but without the enveloping or surrounding myofascial tissue, that musculoskeletal anatomy does not function as we suggest it does. I think that because we're continuing to learn pretty rapidly how the fascial system integrates into the body and how it influences these other systems, the more we continue to learn and the more that we're able to detect and to observe, I think we are going to see a continual shifting of less concentration and emphasis on just the musculoskeletal anatomy and a continual rise in the myofascial anatomy. For the sake of myself and others who have already adopted these concepts, such as Stu and everyone at Altis, a couple of the things that we've observed or speculated on is that the longitudinal myotendinous force transmission only tells us a portion of the story. Again, we'll cover this a little bit in more detail as we go along, but if we think about some of the origins and some of the protocols and procedures to conventional sports science and how we have studied and observed these things, we have to recognize that they have not been a complete view. Particularly speaking, the myofascial lines are going to help with, as this relates to the fascia, particularly the myofascial lines, these are going to play a significant role in movement coordination and what I believe we can kind of term to be generating patterns from shapes. So as Altis has delivered over the years the construct of shapes, patterns, and signatures, I think that the myofascial concepts anatomy fit very well within that, where we want to see the myofascial anatomy as generating our patterns from the shapes that we possess or that athletes possess. Additionally, there's been some really good research, particularly from the Stecco group and then Jan Wilk and Robert Schleip as well, that has suggested that deep fascia may actually be responsible for up to 30 to 40% of total force transmissions. This is a staggering number, and even if we take that as being a little bit inflated and we bring it back down a little bit, and we'll say arbitrarily even 10 to 20% or 10 to 15% of total force transmissions, if we think about that for the concept of elite level athletes, a 10 to 15% difference in total force transmission or output is quite literally the difference between getting cut from the roster and being a all-star or at minimum a bona fide starter. The unique aspect of fascial tissue is its viscoelastic properties, and make no mistake, every tissue in the body and things have a viscoelastic property to them, but the viscoelasticity of fascia is uniquely or distinctly different from other connective tissue structures such as tendons or ligaments, and then also the muscle tissue as well. And with this unique viscoelasticity, fascia provides an elastic recoil effect during movement and dynamics that influences a wide range of things. But to name a couple, we have intermuscular coordination, myotendinous junctions. We have a direct interface and relationship with muscle spindles. This is going to predominantly influence the stretch reflex and stretch shortening cycle, as well as the series elastic component that are going to help to contribute to movement propulsion or impulse. As it's shown here on the left side, we are all familiar with this top graphic here, and we can all get our PTSD from inverse dynamics during biomechanics labs. But we have agreed that this is an appropriate way of measuring and analyzing and observing the body for the sake of performance and for the sake of speed. I think that what I have come to really rely on is overlaying this type of anatomy view with this type of anatomy view. So while we have all of these constituent parts and these segments of the body that are performing very specific things or very precise degrees of motion or very precise velocities of movement, I just look to the integration of those components and try to see the body or see the movement from a more integrated view, and then when it's necessary, work my way down to the more granular aspects from there. This concept of shapes, patterns, and signatures, which was one of the first things that I recall actually learning from Altis directly a number of years back, was really profound for me. And I've mentioned this in other places, but I was never somebody who was very proficient with conventional anatomy. It never made sense to me. I never really grasped it. It wasn't very invigorating for me. I remember vividly sitting in my undergraduate classes and just thinking about how something so sophisticated and so mesmerizing could be so dull and boring in conversation. But to that end, when I came across the shapes, patterns, and signatures concept, it was almost as if things started to click, or if I had the framework to allow myself to understand how the anatomy actually functions. The interesting thing for me about shapes, patterns, and signatures is that it helps me to understand deviation and difference within singular sports, or in this case, across different sports, and how the same actions can be performed in dramatically different ways. So, as it's illustrated here, when we have a 12-year-old female athlete in a sprint pattern and we compare that to an MLB baseball player, for instance, we can see that there's a real significant difference in how these two athletes are performing these sprint patterns. So what that means for me is that when we live and die by our bell curves and our generalizations and our rush to classify or categorize things, I think it allows us to have some things slip through the cracks. While yes, there is a great deal of overlap and commonality in something like linear sprinting, irrespective of whether you're a 12-year-old female or an NFL running back, when we start to look at training prescription, or we start to go through an evaluation process and we're really trying to specifically improve the athlete that we're working with at that moment, we have to understand that there's great deviation across these things, and sprinting being the example here, but really this applies for just about anything. Not only are these things different across different athletes, but even within the same athlete across different time points, we're going to see a great deal of deviation between how the athlete is executing or performing these tasks. This again speaks to the fascial system for me, because when we think about the conventional anatomy, I think we get a little bit siloed to thinking about just a handful of structures. So for the sake of sprinting, we're going to prioritize and analyze the foot patterning. We'll look at the degree of hip flexion or the thigh angular velocity. But when we take a step back and we look at it through the lens of the myofascial anatomy, we can take those points or those certain contexts and then relate them to the other points of interest or emphasis, and then try to bring them together through this unified understanding of what we're actually observing. As it's shown here on the right side of the slide, when we're looking to organize movement through this concept of shapes, patterns, and signatures, we can look at it simply as starting with the shapes being the positions that an athlete occupies in space. So this is going to speak to the static or structural relationships which are going to be built or developed off of their posture, their morphology, different joint positions. If we have an athlete who is coming off of injury, the shape of that injured limb or extremity versus the opposite side and what those differences look like. But essentially, this is setting the border of our puzzle. This is giving us our foundation for movement applications. Patterns then become the connections of the shapes in space and time. So for patterns, we're thinking about the dynamic relationship between the shapes or these mechanical parts, and this is going to be, to name a very small few of them, sprinting, jumping, cutting, or really any other dynamical action that you want to fill in with. So this is essentially what connects our movement, and this is why I see the myofascial lines or the myofascial anatomy as being what generates patterns from shapes, because the patterns are going to invariably require every tissue, every joint that we can really think of or name, and how those all come together to form these patterns. Then finally, we have our signatures. So these are the unique or the individualistic expressions of movement or skill acquisition, and where the shapes and patterns can be reasonably generalized, and we can suggest that there's going to be a decent amount of overlap between different athletes, even across different sports. The signatures are the opposite. They are highly individualized. These are very unique and personal to them. So we're thinking about how someone would throw a pitch or shoot a jump shot. And I think ultimately this is what defines our move. So for the sake of this presentation or for this course, we're going to utilize the 4 C's of fascia as being our heuristic that we're going to work off of. And really we're going to section this thing off as these are listed here between connect, communicate, coordinate, and then finally control. So if we start here simply with connect, this is looking at the structural aspect of fascial tissue. So this is looking at the tangible, literal tissue and then how it is arranged and how it is situated throughout the body. With fascia, we want to think first and foremost about the structural integrity at localized areas. So we can start out by suggesting the plantar fascia and the ankle retinaculum of the foot and the lower leg. This is a structural, tactical, connective tissue that is going to help with mechanical continuity in the global sense. So in other words, the way that our plantar fascia is situated and the tensile properties of the plantar fascia is going to then have a direct influence on how the tarsal bones are positioned. Where the tarsal bones are positioned is then going to essentially determine what our center of pressure is, and then our center of pressure is going to have a wide sweeping effect up the chain with regards to kinetic sequencing and different activation patterns and so on and so forth. From there, we want to think about the fascial tissue as being an epimuscular connective tissue. And this is another one that we'll dive into a little bit more throughout this course. But for the sake of epimuscular connective tissue, we are essentially thinking about the intermuscular and extramuscular connective tissue. We want to think about the epimuscular connective tissue as essentially just playing a support and a synergist role for the bigger contractile structures. I've mentioned it already, but the viscoelastic properties of fascial tissue permit high deformation, so it allows the tissue to be able to be pulled or stretched into end ranges or into different lengths or proximities and then be able to return back to its resting length without deviation or damage. And the other thing with the fascial system that is really important, and it speaks to the structural aspect, is the role that fascia plays in fluid dynamics. So the term that we think about here is thixotropy, which is essentially suggesting that changes in temperature are going to change directly the viscous properties or the fluidity of the tissue. And that is why I utilize so much vibrational concepts and I utilize a lot of manual things for the sake of trying to improve the viscous nature of the tissue. Communicate is going to speak more to our sensory or afferent acuity. So we know that the fascial tissue is highly enriched with sensory motor bodies, and because of this, it's going to play a critical role in the biological communication that's going to occur throughout all kinds of movements and expressions of skill and sport. With this, we're going to think predominantly about proprioceptors, which are going to detect the body's position in space and time, the nociceptive bodies, which are going to be our pain receptors, and then our mechanoreceptors, which are going to essentially be the receptors that detect changes in tension or pressure. And then what I think about with mechanoreception specifically is that it is essentially taking a biomechanical input and then generating a biochemical cascade. Ultimately, for fascial tissue, this is predominantly a collagenous tissue that is going to be driven by activity and stress. So no different than anything else. We recall Davis's law here. The intensity, the frequency, the amplitude, velocity, and direction of force or stress is going to generate a fibroblastic response, which is then going to facilitate the collagen remodeling based on what those stressors or stimulus are. We then have coordinate, which is going to speak more to the motor or the efferent aspects, and this is where we start to think about things that matter more to strength and conditioning coaches. So we're thinking about kinetic sequencing or intermuscular coordination, the premise of biotensegrity, which is essentially the distribution of compression and tension throughout the body, and then ultimately I think that it speaks to the mechanical efficiency of movement, so the ability to couple or decouple based on whatever the actions are. And this leads to control. And I think if somebody were to just say, hey, just tell me straight up what role or responsibility does the fascial system play in movement or in sport or speed acquisition, and I would say that it's probably just the ultimate control system. So it is really intimately related to a number of different biological systems, obviously the musculotendinous system being a predominant one. And with this, the fascial tissue is going to help with movement control. And this is where I think about the movement literacy, the skill acquisition, our mechanical bandwidth. So how much are we able to tolerate and in how many different ways, how we are able to generate pattern formation and then transition between those patterns, what our permitted available degrees of freedoms are. And again, ultimately, this is the interplay between contractile and connective tissue structures.